All right, let's jump straight into this explainer. If you've ever felt like your physics curriculum is just a bunch of totally disconnected chapters, well, prepare to have your mind changed today. We're going to explore how the seemingly invisible world of electrostatics fundamentally links up with 11th grade mechanics. It's like putting together a giant puzzle, and today we're definitely bridging that gap.
Here's the roadmap for our quick journey today. First up, the weight of electrostatics. 2. Basics of electric charge. 3. Decoding Coulomb's law. 4. Beware the vector trap. And finally, 5. Electrostatics meets mechanics. Let's get moving.
Okay, Section 1. The weight of electrostatics. This is a high-yield, foundational chapter.
Let's establish exactly why mastering this topic is absolutely, completely non-negotiable if you're tackling the JEE exams. I mean, think about this. With over 200 questions asked in JEE Main in literally just the last 5 years alone, the weight of this subject is just immense. This isn't just another random chapter. It's a massive foundational pillar. Honestly, if you're playing the probabilities game for your exam prep, ignoring electrostatics is basically mathematical self-sabotage. It is, hands down, one of the highest yield areas you can possibly study.
And hey, it definitely doesn't stop at the main exam. If we look at JEE Advanced over a 15-year span, we're seeing 45 to 50 questions. That makes it an absolute mathematical lock for 2 to 3 questions every single year. Your foundational grip here directly dictates your competitive edge. You've got to know the stuff cold because, well, it's going to show up, guaranteed.
Moving on to Section 2, Basics of Electric Charge. Let's hit these rapid-fire fundamentals.
Before we dive into the really heavy mechanics, we need our building blocks perfectly aligned. So a core fundamental difference between charge and mass is how they react to their environment. Mass and gravity, totally frame dependent. Your weight changes based on where you are. You weigh way less on the moon than on Earth because the gravitational frame shifts. But crucially, electric charge is entirely frame independent. 5 coulombs of charge sitting right there on your desk is exactly 5 coulombs of charge sitting on the surface of the moon. It literally just doesn't care about its location.
So how do things actually get this charge? Well, charges are transferred or generated via these 5 methods. You've got the photoelectric effect, thermionic emission, friction, induction, and conduction. But the absolute vital takeaway here is quantization. Whether you're just rubbing a pen on your sleeve or, using UV light to knock electrons off a metal plate, you are always moving electrons in whole integer quantities. You can't just transfer 1.2 electrons. It's a whole package deal, all or nothing.
All right, Section 3, Decoding Coulomb's law. Let's look at the force between point charges.
So, what actually happens when 2 of these charged particles interact out in an open space? This is where the physics gets incredibly tangible. Coulomb's law formally defines this push and pull interaction, giving us that classic formula we all know, K times Q1 times Q2 over R squared. But hold on. There is a massive caveat here that students constantly overlook. This specific formula strictly applies only to point charges. If you try to blindly apply this to, say, a giant charged rod without integrating, man, you are going to get it completely wrong.
What's really interesting here is the principle of superposition. Think about this rule. The force applied by one charged particle on another is completely independent of the surrounding medium. So, if charge A pushes charge B with 50 newtons of force in a total vacuum, it applies that exact same 50 newtons of isolated force if you were to suddenly submerge them both underwater. Now sure, the net force might change, because the water molecules start exerting their own forces, but that specific, isolated conversation between charge A and charge B, that never changes.
Let's jump into Section 4, Beware the Vector Trap. This is all about the illusion of simple math. Now let's move to where things get pretty tricky. This is where a false sense of security leads a lot of students straight into a brutal vector trap. Imagine a square setup, okay? On the corners, we have a plus Q charge, a 3Q charge, a 4Q charge, and a 10Q charge sitting diagonally across from our target. And we want to find the net force on that single plus Q corner charge. If you calculate the forces from those neighboring 3Q and 4Q charges, it feels super intuitive to just add their resultant straight down the middle diagonal and combine it with the 10Q force, right? Well, as the source educator emphatically points out, a really confident but incorrect answer here is just totally heartbreaking. People rush to answer 10F, feeling super proud of their quick mental math, and boom, it's entirely wrong. Moi moi as they joke. It entirely misses a fundamental, almost invisible rule of vectors.
The trap actually lies in this tiny geometric discrepancy. See, the 3Q and 4Q charges create forces of 3F and 4F. Because it's a classic 3-4-5 right triangle situation, the resultant of those two forces sits at exactly a 53-degree angle from the base. But the square's diagonal, where that force from the 10Q charge is coming from, sits exactly at 45 degrees. 53 minus 45 leaves an 8-degree gap. They do not line up perfectly. You absolutely cannot just add them as scalars. You have to use vector addition with the cosine of 8 degrees. It's such an elegant trap that tests if you're actually visualizing the physics or just crunching numbers on autopilot.
And that brings us to Section 5, Electrostatics meets Mechanics. Time to bridge that 11th and 12th grade gap.
This brilliantly illustrates the ultimate secret of competitive physics exams. 12th grade electrostatics isn't some brand new, isolated world. It's really just a new type of force plugged directly into the 11th grade mechanics you already know. You're just taking that electrostatic push, that pure K, Q1, Q2 over R squared, and tossing it right into your old free body diagrams. You equate it against maximum static friction to find the exact moment a block slips, or against mass times gravity to find when a hanging string goes slack. Electrostatics is just the why the object is being pushed. Mechanics is the how the object physically responds.
Let's actually test this integration with a highly advanced scenario. Imagine a system of 4 charges in a square. Now, you glue 3 of them down so they're completely fixed in place, and you release the 4th one so it's totally free to move. What's the acceleration of the entire system's center of mass upon releasing that single charge? At first glance, tracking all those interacting forces seems like a total mathematical nightmare, right?
Well, here we unlock what the source cleverly refers to as the Balmer concept. It relies on a pretty profound truth of mechanics. Internal electrostatic forces just cancel out. You know, every action has an equal and opposite reaction. Charge A pushes B, B pushes A back. The net internal force of the system is always 0. So the center of mass acceleration relies entirely on external forces, like the mechanical physical force of the hinges holding those 3 fixed charges in place, divided by the total mass. By zooming out, we can completely ignore all that internal chaos.
So how do we actually solve this efficiently? First, you calculate the net electrostatic force only on that single free charge. Step 2, just acknowledge that the 3 fixed charges have an acceleration of exactly 0. Step 3, drop this right into your foundational 11th grade center of mass formula, m1a1 plus m2a2 and so on. Now, because 3 of those a terms are simply 0, the entire terrifying equation just collapses. It becomes just the mass of the moving charge times its acceleration divided by the total mass of all 4 objects. And literally, just like that, you solved a seemingly impossible 12th grade electrostatics problem using a basic 11th grade trick. So, the biggest takeaway here is that bridging these conceptual gaps completely changes the game. It takes these terrifying exam questions and turns them into simple, logical steps. Which really leaves us with this thought: if mastering the bridge between static charges and simple mechanical motion unlocks such amazingly complex problems, what other physics phenomena could this integrated mindset demystify for you next? Keep looking for those hidden connections, and I'll see you in the next